Gravity! What is it? What is this thing called gravity? What is the nature of the attraction between the moon and the earth which keeps them orbiting one another? This mysterious phenomenon which brings things down towards the surface of the earth that we call gravitation. Here's a little size comparison between the earth and the moon. That's accurate. The moon is something like 1/4 the diameter of the earth. Here's the distance between them to scale. And Newton is the one who introduced the idea of a mutual attraction between two gravitating bodies, in this case the earth and the moon, and that attraction can be represented with two vectors which are equal in length and opposite in direction. So the earth pulls on the moon, that's this force, just as hard as the moon pulls back on the earth. The equal and opposite nature of the force may surprise you. Throughout the semester, we will regard gravity as a force, just like any other force vector, whether it's tension, friction, air drag, somebody pushing on something. All of these forces will have equal footing with gravity. It's just like any other F that shows up in the left side of F equals ma. But I would be remiss if I didn't point out that since the year 1915, we've really had a better and significantly more sophisticated way of thinking about gravity. You may be familiar with this visualization where a massive object like a star or a planet is kind of like a bowling ball resting on a rubber sheet, and it creates a depression in that sheet, and any nearby object will roll around in that depression, which is a very appealing way to think about orbits. There's no mention of any force per se. We don't have to draw an arrow to picture this. So this is called space-time curvature, and in the absence of a large mass like a planet, this sheet would look flat. It's the presence of this enormous gravitating body that causes the warping of space-time. And this is how Einstein came to think of gravity. And it's not like that occurred to him overnight. I think it took years of thought and struggle with mathematics to arrive at his theory. Here's another nice GIF of an orbiting body, and you can see that as it moves, it's causing a local warping of the space-time around it. And as I understand it, anything with mass causes warping like that. But the curvature of space-time around a potato sitting in your cabinet is insignificant next to the warping of space-time around something like a star or certainly a black hole. We will be using two different methods for calculating the gravitational force on an object near a planet like Earth. And as a way of starting that discussion, let's consider somebody in free fall. And the most dramatic example I could think of a person in free fall would be back in October of 2012, when some wild man named Felix Baumgartner jumped into the stratosphere from a helium balloon. So this is a CGI trailer of that event, which was upcoming at the time this video was made.
Felix, you are clear to jump at your own discretion. Cleared. I'm on my own. Speed 620 mph. Mach 1.0.
So before long, he has to contend with air drag. But when he initially jumps from that balloon, the atmosphere is very thin up there. There would be virtually no force on his body with the exception of gravity. So here's a still image of Felix mid-flight, and it looks like he's much closer to the surface of the Earth now, but let's continue to pretend that the air drag on him is absent, in which case the only force vector that you would identify in your free body diagram is Fg, and that's not F for Felix, that's F for force of gravity. And of course, we don't have to choose quite such a dramatic example. If you want to experience free fall, you don't have to jump from the stratosphere. You could, for instance, go to Six Flags and go on a ride called free fall.
Oh no. We're still going.
Okay, so during that drop, everybody on the ride and the seat that they're sitting on, all of those things, the people and the seats, are accelerating towards the ground at 9.8 meters per second per second. So we could make a problem out of this where we look at the normal force between the seat and everybody's backside, and we'd find that as soon as they're put into free fall, that normal force goes away. And if we think of the normal force as weight, that means that they would be weightless during the fall. But even that ride is an extreme example. You don't have to go to Six Flags to experience free fall. You could just jump off a diving board. So yes, this man will encounter air drag, especially with that hairy chest. He's going to encounter air drag on the way down to the water. But before he picks up any speed, the air drag is practically zero. We see in this chapter, actually, that the drag force from air depends quadratically on the speed, which means that when your speed is very close to zero, there's essentially no drag force on you. And then the only force would be gravity. So if this guy's in free fall. Even this, though, is unnecessary. If you're a person who likes to run on a regular basis, you experience free fall all the time. I think the definition of running versus walking is that both feet have to be off the ground repeatedly as you're running. So you plant one foot on the ground, then you bounce off that foot, and for a moment, you're in free fall until the next foot hits the ground. So it looks to me like this woman has both feet off the ground. She's in mid-stride. She's in free fall. FG for gravitational force. Let's go back to this guy, though. I like this picture. And we'll choose the usual coordinate system. Up is the positive y-axis. To the right is the x-axis. We don't have to do it this way, but this is the usual choice. And let's apply Newton's second law to this man in free fall, specifically along the y-axis. Let's look at the sum of all the forces along the y-axis, not the x-axis, and we'll set that equal to mass times the acceleration along the y-axis. Remember, you always apply Newton's second law along one axis at a time. You would never set the sum of the y forces equal to mass times the x acceleration. Then you're mixing orthogonal axes. You got to keep them separated. Y acceleration is determined by the y forces. Well, the only force I see is the gravity force. Since it points down, I will give it a minus sign. Fg means the magnitude. That's why we need the minus sign, because we know that this component is along the negative y-axis. And we've already established experimentally that the acceleration is negative 9.8 meters per second per second. Negative because of the choice of coordinate system. If I had put the positive y-axis pointing down, then I would call the acceleration plus g. How do we know it's 9.8? Again, you can measure it. We did it in Tracker. You could also do it very simply in lab if this were a non-lockdown semester. But you should know how to do that. And the minus signs cancel, and we're left with this result. So this method of calculating the gravitational force on an object, just taking its mass and multiplying by the local free fall acceleration, this formula really comes from F equals ma. Try not to forget that that's where it comes from. It's just an application of Newton's second law to the specific case of free fall, where the only force in F equals ma is gravity, and the acceleration is the very special acceleration of free fall. And I said just a moment ago, I called it the local free fall acceleration because remember, that value 9.8 really depends on your location. It depends on your latitude, your altitude, meaning how far you are above sea level. It'll change if you go to the equator versus the North Pole, etc. Here's a common kitchen scale, and on this scale, I'm going to place 1 liter of water. It says Pepsi, but that's basically water. And you'll notice down here that 1 liter of water weighs approximately 2.2 pounds. Now that's only true here on planet Earth. If you took that 1 liter of water over to the moon, put it on the same scale, you would find that that 1 liter of water now weighs only 0.36 pounds, which is about 1/6 what it weighs on Earth. Now, the quantity of water has not changed. The volume of water has not changed. So there's nothing about the matter itself, the atoms, molecules from which this bottle is made, the bottle and the liquid inside it. None of that has changed. What's changed is the strength of the gravitational field in which the bottle is immersed. So most of you probably know that the gravity on the moon is weaker than it is on Earth. And the matter that I was just speaking of, the atoms and molecules from which the liquid and the bottle is made, we call that mass. And I picked this 1 liter bottle because 1 liter of water has a mass of very close to 1 kilogram of mass. Now, I'm just putting arrows here to indicate visually how the strength of the gravitational field here on Earth is greater than it would be on the moon. So we can use a shorter arrow to represent that gravitational field. It points downwards because we know that we're all being pulled down into the surface of the Earth by gravity. Or if you drop something, it tends to accelerate downward. So 1 liter, did you see that? 1 liter of water has a mass of 1 kilogram. So loosely speaking, mass is a measure of just how much stuff a thing is made out of. That doesn't change when you bring it over to the moon. What changes is the strength of the G field, so-called, and as a result, the weight of an object changes. It feels heavier on Earth because the gravity is stronger. So if you took this bottle over to the moon, it would feel lighter if you just held it in your hand. But if you tried to push it, if you tried to give it a push and make it pick up speed, then you could still tell that it's more massive, for instance, than a Cheerio. That's the first thing that comes to mind. So mass has nothing to do with the gravitational field. It's not going to change just because you put it into a different G field. Now, there's a more precise number that you'll be dealing with in the lab, but roughly 1 kilogram here on Earth weighs 10 newtons. In the picture a few slides back, I showed 2.2 pounds. That's about the same thing. 2.2 pounds is about equivalent to 10 newtons. In the US, we like to talk about weight usually in pounds. So if you weigh 180 pounds, your weight in newtons would probably be more like 900 newtons, which makes you sound chubbier, doesn't it? Maybe that's why we go with pounds instead of newtons. So that same kilogram or liter of water brought to the moon will now only weigh about 1.6 newtons. If you take the number 10 and divide it by 6, you get down to about 1.6 newtons. Now, think about this carefully. It's simple, but if 1 kilogram of mass weighs 10 newtons on Earth, wouldn't 2 kilograms weigh 20 newtons? And on the moon, if 1 kilogram weighs 1.6, you would expect 2 kilograms to weigh twice that, or 3.2 newtons. We can keep going in that direction and say that 3 kilograms would weigh 30 newtons. So for each of those examples, well, I'll look at the second one specifically. I said that 2 kilograms should weigh 20 newtons. We'll look at the first example. It tells us that each kilogram weighs 10 newtons. So if I take that ratio of 10 newtons for every kilogram and multiply by how many kilograms I'm dealing with, that will give me the total weight. Simple as that. Take the weight per kilogram times how many kilograms you've got, and that would give you the total weight. So on the moon, each kilogram weighs 1.6. So if you have a mass of 2 kilograms, that would be like a 2-liter bottle of Pepsi. It should weigh 3.2 newtons. Very straightforward. Let's put this into an equation using symbols. And I'm going to use the letter G. Everybody uses the letter G, lowercase g, little g, not big G. G represents this ratio here. It tells you the weight of a 1 kilogram mass in that gravitational field. So here on Earth, the strength of the G field, as you might say, is 10 newtons per kilogram. It just tells you that every kilogram weighs 10 newtons. On the moon, G is weaker. Each kilogram only weighs 1.6 newtons. So here's the equation I was using. I'm using the letter W for weight. That was 20 newtons in this example. And here I've actually got the order switched. I put the 10 newtons per kilogram on the right and then multiply on the left by the number of kilograms you're dealing with. Order doesn't matter, right? 2 times 3 is 3 times 2. I wrote it this way because that's usually how it's written. We put mass first and then the strength of the G field. So what is the G field? One answer to that question is it just tells you how much a kilogram weighs on that planet. Simple as that. So just to summarize, the strength of the G field here on Earth at the surface is about 10 newtons per kilogram. It's about 1/6 of that. Now I've been using W for weight, but with a little thought, I'm sure you'll realize that weight is really the force of gravity on your body. It's Earth's gravity pulling down on you. So consider this person on a scale. If Earth is pulling down on that person, you know, if you just jump off a diving board, what's the effect of that downward force from gravity? The effect is to cause you to fall. You'll pick up speed in the downward direction. So if you're not falling, if you're instead standing on something, that thing must be pushing back on you to balance the force of gravity. So if you weigh 150 pounds, that's like saying that the Earth pulls down on you with 150 pounds. And when you go to stand on the scale, in order to keep you there and keep you from falling, the scale has to push back just as hard as Earth is pulling down. So the scale is also pushing up on you with 150 pounds of force. And that's really the force that gets registered on the needle, or the dial, I should say, or the digital readout if it's a digital scale. So the number that you read from the scale is really the force between your feet and the scale. And that force must balance the force of gravity on you. So we can go ahead and equate, for the purposes of this lab, we can equate your weight with the force of gravity on your body. So I'm just going to relabel that. Instead of saying W equals mg, I'll say F for now. Where it's understood, I'm really talking about the gravity force. If you want to know how hard gravity pulls on you or anything, take the mass of the thing times just the strength of the G field on that planet or moon, or even like an asteroid, let's say. Now, if you were to take a variety of objects and plot the weight of the objects versus their mass, and presumably all these objects are in the same G field, so they're on the same planet with the same moon. So here are 3 points representing mass versus weight for 3 different objects. The first one evidently has a mass of 2 kilograms, and yet it weighs 4 newtons. So if I look at that ratio, an object that weighs 4 newtons when having 2 kilograms of mass, evidently that's 2 newtons per kilogram. So we know we're not on Earth, because on Earth, each kilogram weighs about 10 newtons, which would give us a total of 20. So we're definitely not on Earth. And we're not on the moon either, because the moon was more like 1.6 newtons per kilogram. That's why I wrote mystery planet. So wherever we are, the G field's got a different value there. And let me draw your attention to the fact that 4 newtons, well, that would be, hang on a second. 4 newtons is the height of this blue segment, is it not? And you could call that, if you think back to high school algebra, you could call that the rise. And then the mass, 2 kilograms, that's the length of this segment, which you could call the run. So if you look at this hypotenuse here, I'm really looking at rise over run. Obviously, this distance is the same as the red segment. So 4 newtons over 2 kilograms is the rise over the run. That's the slope. So perhaps the slope here tells us the strength of the G field on this mystery planet. Let's look at the next point. The run here is a mass of 8 kilograms, and that 8 kilograms weighs 16 newtons on this mystery planet. So if I take 16 newtons per 8 kilograms, of course I get the same number. We discover that using this second mass, we get the same value. The G field on this mystery planet has a strength of 2 newtons per kilogram. And once again, 16, that's the height of this bar, that's the rise, and 8 kilograms, that's the run. That would be the same as this red line here. So we can also compute the slope of this line from the origin to here. We get the same number. Obviously, right? Because that's that's a defining characteristic of a line. You can use any 2 points to compute the slope and you'll get the same answer. Whether you compute the slope from here to here, or you compute the slope from here to here, you get the same value. If the slope was changing, you'd be talking about some other type of curve, not just a line. All right, you can check the last one, 24 newtons per 12 kilograms gives you the same number. So I would like to emphasize that what we're really talking about here is G. It's the strength of the gravitational field. On this mystery planet, every kilogram weighs 2 newtons. And you can see that directly from the graph just by looking at the slope. Let's continue. Here's a picture of 2 large rocks. One of them is planet Earth, and the other one, if you zoom in, you'll see is Dwayne Johnson. And yeah, I'm lame. I actually Googled his weight. You know what though? Later I'm going to round this to 300 to make the number easier to work with. But I wanted to be accurate. So if Dwayne Johnson, Dwayne the Rock Johnson, weighs 260 pounds, doesn't that mean that Earth's gravity is pulling downwards on him with a force equal to 260 pounds? So forget about Dwayne for a second. Imagine an actual rock, a big asteroid out in space. And, well, something you'd learn about if you took a physics class or astronomy lecture, I suppose, is that this asteroid gets pulled towards the center of the Earth. So I'm using this red arrow to represent that force. If that force is 1,000,000 pounds, then the length of this arrow would have to be 1,000,000. And I'm using the letter M for the mass of the rock. Now suppose we had another rock that was the same distance from the center. I couldn't put it right on top of that one because that would be confusing. So I put it down over here, but it's supposed to be the same distance from the center that the first rock is. But suppose this rock is 3 times as massive as the first one. So if this mass is M, this one would have 3M. Do you think this rock gets pulled harder towards the Earth? And if so, how much harder? Well, think about it. Just a moment ago, you were, instead of looking at a rock being pulled towards the center of the Earth, you were looking at the rock, meaning Dwayne Johnson. If Dwayne Johnson stopped working out but kept eating the way he normally does, I saw an interview with him one time about his eating habits. It's crazy. If he kept eating like that and didn't work out, wouldn't he gain mass? And then he would weigh more, right? So it makes sense that the more mass this rock has, the harder it should be pulled by the Earth, just the way Dwayne Johnson would be pulled harder by the Earth. So if the rock is 3 times as massive, what's the most obvious guess for how much harder it would be pulled? Presumably, it would be pulled 3 times as hard. Makes sense, right? Now, is that really the case? Do we know that? You probably have to do an experiment to determine that. For instance, you could pour out 1 liter of water into a big jug, weigh it, and then pour 2 liters of water into the same size jug and weigh that one. 2 liters compared to 1 liter would be twice as much mass. Go and see if it's actually twice as much weight. Now that one's kind of obvious, right? I think we all know that twice the amount of water does weigh twice as much. We take that for granted, but we're going to see that similar assumptions about other quantities aren't so obvious. And if we had a rock that was 5 times as massive, yep, I made it look bigger, that should be pulled towards the Earth with 5 times the gravitational force. So what I'm really saying here is that the force of gravity is proportional to the mass of an object. A lot like what we were discussing just a moment ago. In fact, it's exactly like that, really. So over here, 3 times the mass. See how this line segment is 3 times as long as this. So the run is 3 times as long. Well, notice that this red line, which represents the force of attraction, is 3 times the previous line segment length. So tripling the mass results in 3 times the force of attraction. Very straightforward. It's just what you would expect. We have a way of expressing that mathematically. We say that the force and the mass are proportional. Proportionality is a really important concept in the physical sciences, and here's a great example of that. If you plot one quantity versus another, and you find that all those data points fall on a line, then those 2 quantities are proportional. So I would say those are the 2 best ways that I could define proportionality. If 2 things are proportional, it means when you plot them versus each other on a Cartesian graph, you get a line. You could also just say doubling one causes the other to double, or quadrupling one causes the other to quadruple. Basically, if you multiply one by any factor, the other one will increase or decrease by the same factor. That's what it means for two things to be proportional. This is not an equal sign, that is the proportionality sign. And you should know what that means. Here's an example of two quantities that are not proportional. You already recognize this is a parabola probably. So for this particular mass, we've got a certain force associated with it. Let's just suppose that you're, I don't know, you're in some weird universe where gravity behaves differently. And now I'm looking at something that's twice as massive. So the blue line up here is twice as long as the blue line here. But look at the vertical coordinate now. If I put in that red line, you see how this red line is 4 times as long as this red line. So in this hypothetical universe, doubling the mass resulted in a force of gravity, gravitational attraction that's 4 times as great. Those two quantities are not proportional. Doubling one causes the other to go up by a factor of 4. So these two are clearly not proportional, but turns out that's really not how gravity works. As far as we know, the force of attraction is proportional to the mass. So here's a really creepy graphic I pulled up showing a, relative sizes for children and adults. Man, these people look like aliens. But here's, I don't know, somebody approaching adolescence. Let's say their mass is m. Here's a larger person, an adult who has twice the mass, let's say. And this is so simple. We all know this, but if this person really has twice as much matter in their body as this person, then when they get on a scale, they're going to find that this second person, the adult, weighs twice as much. So if you weigh 200 pounds and your kid sister weighs 100, that means you have twice the matter, twice the mass in your body that your kid sister has. Back to this graphic. Instead of looking at how the force depends on the mass of this asteroid, let's vary something else. Let's change the distance between the asteroid and the center of the Earth. So I'm going to use the letter R, like most books. Most of the time we use the letter R to denote the distance between masses, not D for distance. So R is just kind of historical. And what happens to what happens to F if we change R? So instead of a more massive asteroid like before, let's take the same asteroid and put it twice as far. Notice I'm looking at the distance from really the center of the asteroid to the center of the Earth. You see how this distance is twice the original distance. Will this rock get pulled towards the Earth just as hard as this rock? Hopefully you can see it's got to be less, because if you took this asteroid really far away, like another light year away, eventually it's not really going to be pulled at all by the Earth, or with negligible force. It'll be pulled harder by some other planet or star and fall in that direction instead of falling back towards the Earth. So we know that as you go really far away, the gravity has to decrease. How exactly does it decrease? How quickly? That's what we're trying to answer here. So perhaps the most obvious guess would be half. If you go twice as far, maybe it's 1/2 the force. We know it's not twice the force, because that would mean that the force goes up with distance. This is the opposite. If the distance goes up, the force should go down. So they're definitely not proportional. In fact, they should be inversely proportional. Perhaps. I'm suggesting that's one possibility that sort of makes sense. So suppose you've got an asteroid at distance r. I didn't really specify the distance. We don't need these numbers, so just ignore those. You're out at this distance r, and there's a particular force represented by the height of this bar. Okay, this red bar represents the strength of the force. If we now go twice as far out, not twice as far, 5 times as far out. So we're way out. Take your asteroid and put it way out at 5 times the distance that it was originally. See how this blue line is 5 times as long as the original blue line? Well, all we have to do is look at the curve, which suggests that now the force would be only 1/5 of what it was originally. This is what we call inverse proportionality. If you put the asteroid out at 5 times the original distance, just take the reciprocal, you might expect that the force is now 1/5 what it was at the original distance. So it's plausible, right? It does make sense. At least force is going down as distance goes up Is it correct, though? Well, let's look at a numerical example. See how I've rounded the rock's mass up to 300 pounds. Maybe he's on holiday. He went a little crazy Thanksgiving weekend or whatever. Suppose he weighs 300 pounds. That means that Earth's gravity pulls on him downwards with a force of 300 pounds. Well, let's now put him twice as far from the center of the Earth as he is at the moment. Of course, this is not to scale, right? You can't even see the rock at this distance from the Earth. So the distance between him and the center of the Earth is basically Earth's radius. Let's put him out twice as far. So imagine he's standing on some ginormous platform that goes way up into the sky, and see how I tried to do it so that the height of this platform is the same as the radius of the Earth. Here's the radius. That's from the center to the surface. So I went that distance again, way up above the atmosphere. If gravity works the way I suggested in the previous slides, then since he's now twice as far from the center, his weight should be half what it was. And so instead of weighing 300 pounds as he does on the surface, you might expect him to weigh 150 pounds. And if you actually had a way of constructing a platform like this, you could take a scale up there and check this. But you would find it doesn't actually work that way. Now, fortunately, we can answer this question without actually constructing this platform, because that's never been done. That would be an incredible technical challenge. I don't know if that will ever be done. We still don't have flying cars even, so that's not how gravity works. Well, then how does it work? If it's not an inverse proportionality, then what is it? Well, the very next guess might be your correct one, or your next guess might be, what am I trying to say here? If it's not 1 over distance, perhaps it's 1 over, I don't want to give it away, but here is the answer. He would weigh 75 pounds. So how does that work? If you went from 300 pounds to 75 pounds, what, do you just always divide by 4? Or is there a deeper connection there? A more significant connection. Notice that 75 is 300 divided by 4, but 4 is 2 squared. So he went twice as far out, and his weight got divided down, not by a factor of 2, but by a factor of 2 squared. And I probably should have some more examples in here, because we can show that if he went 3 times as far, 3 squared is 9, he would only weigh 1/9 of what he does at the surface. So 1/9 of 300 is something like 33 1/3 pounds, or it's exactly that. Okay, so that's really how gravity works. It's not inversely proportional to the distance, it's inversely proportional to the square of the distance. If we took the rock 10 times as far from the center of the Earth, way out into space, 1 over 10 squared is 100th. He would weigh 100th, or only 3 pounds, believe it or not. Okay, so this is called the inverse square law, and maybe the first person to ponder this possibility was Isaac Newton. And if you take a physics class, you can learn how he actually watched the behavior of the moon. He watched how the moon falls around the Earth and was able to deduce that the gravity out at the moon really is 1 over r squared, what it is at the surface. So it's been a few hundred years that people have understood that this is how gravity works. So here's a plot of that inverse squared dependence here. When you're starting out at a distance r, that could be the surface, so your distance from the center of the Earth would be just the radius of the Earth. And there's a particular force on your body, we'll call that F. If you could now go out to a distance 2 times the radius, so you're now twice as far from the Earth's center as you are when standing on the surface, now the force on your body would only be 1/4. If you go out 3 times as far, you're talking about 1/9. So it drops off more rapidly than a simple inverse proportionality. By the time you're 5 times as far, you're not 1/5 of your original weight, you're 1/25. So we say that the force of gravity falls off like 1 over r squared. That's one way of saying it. It drops off like the inverse square. Back to this graphic. What are we doing now? Well, I've been pondering an asteroid getting pulled towards planet Earth, but what if we replace planet Earth by, oh, I'll get to that in a second. Wouldn't this thing have a tendency to fall towards the Earth? because of the gravity. So if it's just going to be chilling there, if it's not moving, I guess we have to imagine that there's some invisible hand holding it there. And if you were to let go of that asteroid, then you would expect it to fall towards the Earth, and it would pick up speed the whole time and be very devastating when it did strike the surface. So now, yeah, let's replace Earth by an enormous asteroid, and we can imagine same thing, right? If we were holding this asteroid and then we released it, we would watch it slowly fall into the ginormous asteroid. Now, this is misleading because if something actually is this massive, you can tell the way I have presented it here, it's even bigger than the Earth. Well, when things get that big, the gravity within is so strong that it crushes this thing into a spherical shape. So it's actually misleading to have something more massive than the Earth with this irregular shape. I believe that's one of the definitions of a planet. It has to be massive enough so that its gravity is sufficient to draw itself into a spherical shape. What we normally think of as rock and metal, or we normally think of rock and metal as being extremely rigid. You can't pick up a rock in the palm of your hand and squish it into a sphere. But when you've got something this big, believe it or not, the gravity is strong enough to do that. I don't know how quickly that happens, but okay. Well, let's look at a limiting process here. We're expecting that this thing would fall towards the much more massive object, because when you drop a pencil, the pencil falls towards the Earth, not the other way around, right? Well, what if we made this asteroid smaller? It's still quite a bit bigger than this one. So if we let go of this rock, we would expect it to fall towards this rock. But if we continue this thought process, eventually it becomes ambiguous. By the time we get to this, why should this one be the only one that moves and not this one? If they're comparable in size, would they not be pulled towards each other? Would it not be mutual? So this leads us to the next dependence of gravity on mass. So you can imagine now that you'd have to hold both of these and hold them against their mutual gravitational attraction to prevent them from falling towards one another. And I'd like to say one more thing about that. Maybe you're wondering, how long would that take? If you actually took a couple rocks that you could hold in your hands, held them a few feet apart, and released them out in outer space away from any other planet or star, are they just going to smash together in half a second, or is it going to take 10 years? Well, you can actually do that calculation using some of the physics that you would take in an introductory physics class, a little bit of math, and it only takes a couple hours. It would take on the order of, 2 to 3 hours, maybe, for those two rocks to fall together. Okay, I've got the rock standing on planet, the rock is in Dwayne Johnson, standing on Earth, standing on the moon, and I'm reminding you that the gravity on the moon is weaker. That's why I've made this arrow shorter. Why is that? Why does the rock weigh less on the moon? Why is the force of gravity on his body less on the moon? Well, I think this picture makes it fairly obvious, because the moon is way less massive. So we already established that if Dwayne Johnson stopped working out but kept eating the way he does, he would gain mass and hence he would weigh more. But you could also change his weight, not by changing his mass, but by changing mass of the thing that he's standing on. So over at the moon's mass is so much less than the Earth's mass that it doesn't pull on him as hard. So evidently we've totally been ignoring the other mass in this equation. We've talked about how the rocks, or Dwayne Johnson's mass, affects the force of gravity, but what about the mass of the thing he's standing on? So we go back here, and now we see that not only does this thing get pulled harder if it's more massive, but this thing should also get pulled harder if this thing is more massive. Both of the masses should matter. So what I'm doing here is I'm shrinking this mass and showing that the resulting force of attraction on the other mass should decrease. The smaller the left asteroid is, the weaker the gravity force on the asteroid on the right. But what's so special about the one on the right? Can't we repeat that argument for the one on the left? So the more you think about it, the more you realize this really needs to be a mutual attraction. These two have to pull on each other. And one of Newton's great insights is that the force of attraction has to be equal and opposite, which is kind of surprising. You might think that this big one will pull harder on that one because it's so much bigger, right? It's kind of like tug of war. You imagine playing tug of war between a small person, I don't know, maybe like an 8th grader, and a fully grown bodybuilder. And you might think, well, the bodybuilder can pull way harder on the 8th grader than the 8th grader can pull on the bodybuilder because the bodybuilder is so much stronger. Well, surprisingly, and this is really a topic for a physics class, when you play tug of war, you don't actually touch the other person, right? You're not pushing on them or pulling on them directly. You're pulling on the rope. And it turns out that the tension within the rope is the same in both people's hands. So, you know, even if you're smaller, if you're less massive than the person you're playing tug of war with, if you pull hard enough, you're really just going to pull yourself off of the ground. So the only way to win tug of war is actually to have sufficient friction between your shoes and the ground, or if you've got cleats on, then you have a real advantage. But that's really another topic. The point here is that gravity is a mutual attraction. They're both pulled towards each other, and those two forces are, we say, equal and opposite, which is slightly ambiguous language, because how can they be opposite if they're equal? It just means that strength is equal. So if this one's getting tugged with 2 billion pounds of force, this one also gets pulled with 2 billion pounds of force, but the forces point in opposite directions. And now the interesting conclusion there is, and I don't have a graphic for this, but again, if you weigh 200 pounds, when you jump off a diving board, you fall towards the earth because the earth is pulling on you with 200 pounds force. So suppose this is you having jumped off the diving board. Here's planet Earth. As you're falling towards Earth, you're being pulled with 200 pounds. Well, guess what? You're also pulling back on the Earth with 200 pounds. So why is it that the Earth doesn't fall towards you? Well, there's a whole bunch of other people also living on planet Earth, and they're pulling it in different directions. So there's that. But you can imagine a perfectly spherical, not like this, perfectly spherical planet with just one thing on that planet, you. And you might imagine that if you're falling towards that planet would be falling towards you. And in fact, it would be. But it would be picking up speed so slowly, it would be impossible to measure. It would be a speed so low or an acceleration so low, there's no way you could detect it. So for all intents and purposes, no, it doesn't move. But if you made that planet small enough, you might actually be able to detect the mutual motion towards the what you would call the center of mass. Okay, so we really need to look at both masses, and that's why we need some labels here. Let's call this one mass 1, over here mass 2. You could also call them mass A and mass B, or big M and little m, whatever. But notice I've drawn these arrows equal in length, opposite in direction, and I'm calling them both, I'm calling them both F, because they have the same magnitude. I think we've established now that the force is proportional to this mass. So if I tripled mass 1, so now this asteroid on the right is 3 times what it was originally, then we know that it's now going to be pulled 3 times as hard. That's just like saying that if Dwayne Johnson stopped exercising and ate like a pig forever, he might actually double his mass, and then he would weigh twice as much. So the force is proportional to this mass, but because it's reciprocal, then the same reasoning applies to the other mass. So going from here to here, let's now imagine that we've doubled, not tripled, but doubled this mass. What's the overall resulting force between them compared to what it was originally? So we tripled one mass, we doubled the other mass. Well, since the force is proportional to both of those masses, the effect of multiplying by 2 and then multiplying by, I got that backwards, the effect of multiplying by 3 after you've tripled this mass, and then multiplying again by 2 after you've doubled this mass, the overall effect is to raise the force of attraction between them by a factor of 6. So the way we summarize that is by saying that force is actually proportional to the product. We say the product of the two masses. See how if you plug in 2 times m1 3 times m1 and 2 times m2, overall you pick up a factor of 6 out front. 3 times 2 is 6. Let's bring together now the two very important discoveries that we've made here. We've got two simultaneous statements of proportionality. We know that the force of attraction between two masses is proportional to the product of the masses, which is a way of saying that it's proportional to each of them individually. But we've also got this inverse square law. We know that the force depends on the reciprocal of the square of the distance. So rather than make these statements separately, there's no need to do that. We can combine it all into a single statement of proportionality. This is a result you can find in any introductory physics book. You can say that if you just want to express it all at once, you say that the force of gravitational attraction between two masses is proportional to the product of the masses and inversely proportional to the square of the distance. And that's normally called Newton's universal law of gravity or law of gravitation. The word universal is supposed to emphasize the fact that it doesn't just apply to the force between a moon and the earth, or even the sun and Jupiter, let's say. It also should apply to something like an apple, which fell from a tree and is accelerating towards the surface of the earth. Because in Newton's time, even among scientists, I think there was a distinction in people's minds between what happened here on the earth and what happened way out in space, or the heavens, or the celestial sphere, however you'd like to think of it. And so they may have thought there was a different set of laws that governed earthly phenomena and things that happen out in space. You know, every night people could see the planets against the background of the stars, and they noticed that the planets drifted from one week to the next. And Newton may have been the first person to be really convinced that the same laws should apply way out there and down here on good old Earth. Hence the universal law of gravity. Now, I've been expressing it with this proportionality symbol. What if we'd like it to just be equal sign, so that we can actually calculate the absolute force for any given mass? Like, we just plug in numbers for the kilograms, or for the masses and the distances, and predict what that force would be. Well, if that's the equation, if that's the way it works, let's investigate that. I've already pointed out that 1 liter of water or Pepsi has a mass of 1 kilogram. So let's imagine we're way out in space. We don't have to compete with the gravity from planets. We're just interested in the mutual gravity between these two things. And let's put them 1 meter apart, which is a little over 3 feet. So that's like holding them out almost at arm's length from each other. And let's plug those numbers in, because these are the standard SI units that physicists, that's a tough word, physicists, that they use. So let's plug in those numbers into this formula. Well, that would just be mass times mass over distance squared. Since all the numbers I chose are 1, what is 1 times 1 over 1 squared? I'll let you take a moment. If you have to use your calculator, go ahead. See if you can do that on paper. You know, carry the 1, go to the tens place. Got it? Okay, 1 times 1 over 1 squared is 1. Now, if you plug in standard units, what comes out is also, I should say SI, we call those SI units, is also a standard or SI unit of force, which is not the pound, it's the Newton. Okay, so evidently, if this is the correct equation, these two water bottles, separated by a little over 3 feet, they should pull towards each other with the force of 1 Newton. So maybe you're wondering, well, how much is that? Is that a lot? That's about 0.22 pounds. You might want to memorize, you don't have to, but a Newton is a little less than a quarter. Quarter of a pound. Okay, is that a lot? Think about the consequences of that. And the reasoning here, it doesn't just have to apply in outer space. You could make the same calculation for 2 water bottles separated by 1 meter here on Earth. Here they are, pulling on each other with that mutual force of 1 Newton. Let's put them on Earth. Say they're on a table, and in your mind, maybe you should rotate these 90 degrees so that they're free to actually roll. Don't you think if these two were pulling on each other with that force, wouldn't they actually start to roll towards each other? I mean, a quarter pound is, you can feel it, right? When you go to Burger King and order a quarter pounder and you put it in the palm of your hand, you feel the weight of that burger. It's it's not as much as you hoped it would be, but a quarter of a pound is significant. I think you would definitely see these two water bottles roll towards each other. And keep in mind, as they get closer, the force would actually go up. They would pull on each other even harder. Have you ever seen something like that? Does that sound realistic? And that's just 1 kilogram. Imagine 2 people. Imagine Dwayne Johnson and like the Hulk, to pick an old example, standing 1 meter apart. They would feel many more pounds of attraction between them. We just don't see that sort of thing. The consequences are ridiculous when you think about it. So there's something suspicious then about this equation. It's not correct. Clearly, it doesn't lead to physically realistic results. So what's missing is a number out front, which we call a constant of proportionality. And how do we know that number? Can we just reason our way to the answer? Well, it's really something you would have to measure. It's something you would have to go out and determine experimentally. You could do it theoretically with these water bottles. If you had an extremely sensitive force measuring device, maybe you could hook up some springs to an electronic sensor and actually determine the force between those. Well, it's really difficult to do that even in the year 2020. So you can imagine in Newton's time, in the early to mid 1700s, nearly impossible to pull that off because we know the force is so weak. So Newton, left this world not actually knowing what this number was. He had not successfully measured it. Well, the first person to measure it was somebody named Cavendish. Not too long after Newton kicked the can, but that's a long time ago, right? Over 220 years ago, somebody first successfully measured this using what's called a torsion pendulum. Pretty ingenious method. I'll let you read about it if you want. The basic concept behind it is pretty easy to understand. You can do this in just a regular physics class. I've never actually done this lab because it takes several hours to collect the data. It's kind of tedious, but believe it or not, here at Long Beach City College, we have a dusty apparatus that's been sitting in the stockroom for decades. And when I get around to it, I'm going to take it out and measure what we call big G, that constant of proportionality. And here it is. Here it is. If you could measure the force of attraction between 2 Pepsi bottles 1 meter apart, you would find that the force of attraction between them, this is totally backwards. This says 10 to the 12th. It should say negative 12th. So let me fix that and get back to you. I really needed to make 2 corrections. First was changing the exponent from 10 to the negative, or 10 to the positive 12th back to 10 to the negative 12th. And then also I changed it from 60 to 70 because I wanted to round this to 1 sig fig, and that 6 would cause this to round up to 7. So what I've done here is move the decimal point 1 to the right, which is like multiplying by 10, right? And I have to pay for that by dividing by 10. And that means lowering this power by 1 from negative 11 to negative 12. So the reason I chose to go with 12 is because then you can say 70 trillionths of a Newton. And I goofed again. This should have units there. It should say Newtons. Let me fix that. Incredibly small force, is it not? How could you ever hope to measure a force that small in a laboratory for objects like this? You'd need a very clever device, very sensitive devices. So if you're interested, read about the torsion pendulum and what Cavendish did. Now, this force, the only way to make this force large, something you can actually feel, easily measure, is to have one of these objects be much more massive than just a liter of water. Where's my laser pointer? So, for instance, you could make this bottle of water the size of a planet. If you had a planet-sized object and a water bottle, then you would feel the force, because isn't that exactly what's going on when you hold one of these bottles in your hand? You're feeling the attraction between the bottle and the other mass, which is planet Earth. And that's a much larger force. But check it out. The force law that we arrived at was some number, some constant of proportionality that must be measured times the product of the masses divided by the square of the distance. And I've just told you that if you have 1 kilogram and 1 kilogram right here, separated by 1 meter, square that the force that comes out is basically 70 trillionths of a Newton. So by sticking this number in front, we force the equation to work because this equation is now true, is it not? This tiny number times 1 over 1 squared is just that tiny number. So the left side and the right side are equal. We've fixed the equation. And if you're curious about the units, there they are. So we call this big G. This is the universal gravitational constant. As far as we know, you can measure that here on Earth, or you can measure it at the edge of the solar system, or you can go to the other side of the observable universe. And I'm not a cosmologist, but I think the understanding is that number is going to have the same value everywhere. Now, if you go get a PhD in cosmology, you may discover that I'm somewhat wrong about that because things get very abstract and confusing as you go deeper into all of these questions. And I'd like to point out before we move on that once this number had been measured, measuring this number amounts to weighing the sun or weighing the earth. As soon as the value of that number was known, humans now had an approximate value for the mass of the sun. And by the end of the semester, you'll understand exactly what that means and how that's done. Really, you just have to time the orbit of satellites. If you look at how quickly the moon whips around the earth and you happen to know the value of big G, you also have to know how far out the moon is, then you can actually calculate the mass of the earth. Okay. So here's the law again, Newton's universal law of gravity. Here's the value of G, which you actually will need to do this lab. Let's return now to Dwayne Johnson standing on the earth, or anybody. And let's, these two masses now we'll think of as Earth and the person. So M1, M2, if you want to do it that way, or we could just relabel it and use big M and little m. Big M obviously for the Earth and little m for Dwayne Johnson. And then, as I was saying earlier, if you look at this to scale, a person is so tiny compared to the Earth that their distance from the center is basically Earth's radius. So Dwayne Johnson's distance to the center of the Earth is really just the radius of the Earth. So that I plugged in that particular value of R. And now we've got a nice formula for calculating the force of gravity on Dwayne Johnson. In other words, his weight. Here's a totally different way of calculating something's weight. It's a lot more elaborate than what we looked at towards the beginning of this presentation. And it works, think about it, it works for any spherical planet. If you know the mass of the planet and the mass of the person and the radius of the planet, and you happen to know the value of big G because thankfully somebody else did the measurement for you over 200 years ago, you can plug all those numbers in your scientific calculator and calculate their weight, which is really the force of attraction between the person and the planet. Now, at the beginning of this presentation, I presented this way of calculating weight. You have to know the strength of the G field on the planet. That's how much each kilogram weighs, right? On this planet, it's close to 10 newtons for every kilogram. On the moon, remember, it was like 1.6 newtons per kilogram. And then you multiply by the person's mass. Now you've got their weight. Well, here's a new formula for calculating their weight, which seems to be more difficult, right? You have to know some additional information. You need to know the mass of the planet they're standing on and the radius of the planet. And you have to have this pesky small number. Well, if both of these give you a person's weight, if they both give the same number, then those formulas should be equal to each other, right? If they give the same result, we can set them equal. And you'll notice they both have a common term. The mass of the person appears on both sides. And that means we can divide that quantity out. Doesn't even matter. And here we have, interestingly, a formula for predicting the strength of the G field at the surface of a planet. All one must know is the mass of the planet, the radius of the planet, and the value of big G, which presumably is the same everywhere in the universe. How cool is that? You can calculate the strength of the G field at the surface of any planet. And I will do an example calculation for you. So the 10 newtons per kilogram that I was discussing here on Earth, that's something that's measured. You just have to go get a scale. And if you know you're dealing with 1 kilogram of mass, maybe it's a chunk of aluminum or whatever, you just plop it on the scale and weigh it. You find that it weighs almost 10 newtons. Well, here's another way to get that value theoretically. So here's the formula, again, off to the side. And why should it only apply to planets? Seems to me, hopefully it seems to you, that you could You could use it for any spherical object. Now, why does it have to be a sphere? That involves a little more math. So if you took a physics course, you might get to explore that, but it doesn't work so well for lumpy shaped objects. This formula works for spherical objects where the density is uniform. You could use it to calculate the acceleration at the surface of a moon, or even, I think Ceres is the largest asteroid in the asteroid belt. How cool is that? You just have to know the mass of the object and the radius. So M and big R change as you go from one of these celestial bodies to the next. But what doesn't change is big G. That's why they call it the universal gravitational constant.